Bismillahirrahmanirrahim. So we're still talking about the link state routing protocols and OSPF. So I would recommend, you pay attention to the differences between the OSPF and EIGRP. There are some minor differences that makes that you need to pay attention to. Okay, so I go through these differences a lot, and I try to highlight them so that you don't get confused. For OSPF, for example, we have again the hello protocol, and the hello packets are sent every 5 seconds, similar to EIGRP. However, for again, similarly to EIGRP, the OSPF uses the multicast to send hello packets, and again, hello packets are sent using one hop broadcast, okay, which is different from flooding, and we talked about the difference between the two. The hello packets are sent for the non-broadcast multi-access networks, and we said that this multi-access network is the network where you have multiple routers are connected using a switch, in which case it's a logical mesh topology, and for that particular topology, because it's a bit challenging, usually sending hello packets every 5 seconds would cause significant amount of overhead, and that's why EIGRP uses 60 seconds, whereas OSPF uses 30 seconds as a frequency for the hello packets in non-broadcast multi-access networks. The dead interval corresponds to the hold time in EIGRP, and that's the duration of time where a router should wait for receiving hello packets from the neighboring routers. If it does not receive hello packets within that duration, then it declares this router as dead or down. So the dead interval for EIGRP used to be 3 times the hello interval, and for OSPF it's 4 times. Okay, so these are minor differences between the two. As we have discussed last time, we have the concept of designated router and backup designated router, and we said that the concept of backup is that in normal cases it's not being used, and the concept of designated router and backup designated router is only used for the case, again, of the non-broadcast multi-access networks. Because as we said before, if you have a topology like this, then you create a logical mesh, and then to send hello packets one time, every router has to send a hello packet which produces n times n-1 messages being sent over the network, which is huge overhead. So instead, designated router is a special type router that receives hello packet from all routers in using one message only, and then the designated router will send it to all the other routers. So that saves the amount of messages being broadcast on the network to n messages as opposed to n times n-1. So the backup designated router, as we said, is it takes over the designated router in case that this designated router fails. Okay. So there was a question last time regarding the election process. How do we select a designated router to be the designated one? And I said that there is an election process that has to run between the routers, which is out of the scope of the course. Okay, but basically it's based on like some router ID or something like this. So we know that each router has a specific router ID. So you can elect the router ID that has the highest router ID or something like that. You can select the router that has the highest router ID, or Specify any type of criteria that can be used for election. But again, this is out of the scope of this discussion. Continuing the type of messages that that OSPF uses, we talked about, of course, the hello message. We talked about the database description, and we said that database description is used to synchronize the link state database between the routers. So if a router wants to check its own database against the neighboring router database, then it sends a database description with only the ID of the link state of any route. It's similar, as we said, it's similar to IMAP when IMAP displays to you only the header of the email, not the actual content of the email. It does not bring it from the server. So same thing, you send a message with like brief identification of all the link state information that you think you would have or you wouldn't have, and then you check yours against the router next to you. Then based on the response, you may actually send a link state request to request the content of a specific link. Okay, so that will bring you the content of the information, which will then include all the cost and link type and all this information. Okay. When you send the request, you receive the response in a form of link state advertisement or link state update. So this message is called link state advertisement or link state update. Those two names are used interchangeably, so you can use any one of these two names. So LSU or LSA, they both mean the same thing. And what that means is that when there is a topology change, or when you get requested to send the content of a specific link, then you send the content of the information of the link state in a form of link state update. So you send it, and as we said, the link state update uses a flooding, which means that the link state update will propagate through the entire network. Okay, not just broadcast to the neighbor, but all the neighbors will actually forward the same message as is to all the other routers and so on until it propagates through the entire area. When you send the link state update, then you get the acknowledgement. These types, you don't have to memorize or to know anything about this. These are specific link state advertisement types, but we don't have to go through this, so you don't have to really know more information about this, okay? So OSPF, as we said before, uses the Dijkstra algorithm. So the step that we have done so far is that we have made sure that all the routers, they have link state database that has information about all the links in the area. Okay, and the idea of sending messages as like hello to discover and create the adjacencies. So hello to discover neighbors and create adjacencies, and then we send link state request or database description to make sure we synchronize the database, and then we send link state advertisement or link state update to propagate or to exchange the detailed information about all the links in the area. At this step, we have all databases of all routers. They have information about all links. So what happens is that each router individually will then run the Dijkstra algorithm against its own link state database. Dijkstra algorithm creates what we call the shortest path tree, okay, starting from that router. Okay, So starting from that router, how can we get to every single destination in the network? How can we get to every single destination network in the area? Okay, so from router 1 to destination 10.0.0, from router 1 to network 172.168.0.0, from router 1 to X to Y to Z, and so on. Okay, of course, from router 1 to each of these networks, there could be multiple paths, and the job of the Dijkstra algorithm is to get you the shortest path to go from any point to any point, from one single point to any point in the area. This is what we call the shortest path tree. From the shortest path tree, I can simply create the routing table. So I know from router 1 to network 10.0.0.0, the cost will be, for example, like 100, and the next hop will be router 2. So I can get this information directly from the shortest path tree. So these are the three major steps that OSPF needs to perform in order to create the routing table. So EIGRP does not have to create or host or maintain any database other than the routing table, right? And that's why we said that OSPF uses more memory and more processing, at least at the beginning or at the startup of the network. Okay? Any questions? So another minor difference, as we have discussed for EIGRP, we used to start EIGRP by saying router EIGRP and process ID, or administrative distance, as we have called it there. And we said that the administrative distance actually functions as a process ID to identify the instance of EIGRP process that runs on the router. And we said that one very important condition on EIGRP instances on multiple routers, that they need to have the same process ID or administrative distance in order for them to exchange routing information. So if two instances are running on two different routers and they don't have the same administrative distance, then they are not neighbors. They cannot exchange any routing information. Okay? So OSPF here uses process ID. However, the difference here is that this process ID has only local significance. And there's no such condition that the process ID between two OSPF instances have to match. Okay? So that's a difference between OSPF and EIGRP. So just the fact that you specify a process ID here, it doesn't mean that this process ID has to match with another OSPF that runs on another router. Why? Because we use the neighboring router based on the area ID, not based on the process ID. Because we said that OSPF uses the concept of area, which is a subdivision of the autonomous system, right? So the autonomous system is subdivided for OSPF, is subdivided into areas, right? So any two routers in the same area are neighbors. They can exchange routing ID, regardless of whatever process ID they use. ماشي كده? That's a difference between the two routing protocols. So we specify the area ID when we start setting up the networks on each interface. Then we say that this interface belongs to this area, this interface belongs to this area. And as long as there are two neighboring routers on the same area, they can exchange routing information. Okay? Any question, any confusion in this point? Okay, so that's another difference between OSPF and EIGRP. The last point that we need to discuss here is the metric for OSPF. And that's another main difference between OSPF and EIGRP. If you remember, the EIGRP used to use at least the bandwidth and delay, right? Bandwidth we used to calculate the bandwidth based on the minimum link bandwidth across the end-to-end path, right? And we used to use a reference bandwidth of 10 gigabits per second, right? 10 gigabits per 10 to the power 10, okay, as a reference bandwidth. OSPF works slightly different in that case. So the first difference is that OSPF uses 100 megabits per second as a reference bandwidth. So that changes the calculation slightly. And the other difference is that OSPF uses the cost as the accumulated bandwidth across all the links end-to-end. Across all the links end-to-end. Okay? So the cost of so each link will calculate the cost based on 10 megabits per second divided by the bandwidth of the link, right? So if the bandwidth of the link is, if the network, for example, is Ethernet, and Ethernet like 100 base T, which means that the theoretical bandwidth of this network is 100 megabits per second. Because the reference bandwidth is also 100 megabits per second, so the cost of the Ethernet is 1. Okay? So for an Ethernet of 10 megabits per second, which is 10 base T, then the cost is 10. Okay? If you have like a T1 connection, a T1 which is 1.544 kilobits per second, then the cost is around 64, which is 10 to the power 8 divided by 1544 thousand bits per second. So the cost in that case is 64, and so on. So that's how we calculate the bandwidth. EIGRP used to multiply this by 256, if you remember. We don't have to multiply here by 256. Okay? We don't have to use the delay. OSPF does not use the delay in any way. Okay? And the other major difference in calculating the metric for the case of OSPF is that if I want to send from R1 to here, then I have to accumulate the cost across all the links. So the cost on this link is, for example, 64, and the cost on this link, because it's Ethernet, the cost is 1. And as we can see here, if R1, this is R1, if R1 wants to send to 10.10.10.0, which is this network, okay, then the cost is 65. See that? This is the total cost. And the cost here is accumulated. Again, it's accumulated. Unlike EIGRP, because in EIGRP we use the link that has the minimum bandwidth, in which case we use the bandwidth of this link, because it's less than the bandwidth of this link, so this will be the bottleneck. And we calculate the bandwidth part of the metric based on this link only. Okay, and then we take the two links into account only for calculating the delay part, not the bandwidth part. Here, because we don't use the delay, we have to accumulate the bandwidth of all the links. Okay, so the total cost here is 65, which is 64 plus 1. Okay, something we notice here is that we have the bandwidth here, which is 64 kilobits per second. And here we have a bandwidth of 256 kilobits per second, and here we have 128 kilobits per second. Actually, this is not the theoretical bandwidth of this link. The theoretical bandwidth of all these links is, because they are all T1 connections, the theoretical bandwidth is 1544 or 1.5 megabits per second for a T1 connection. The highlighted bandwidth here is what we call the actual bandwidth. The actual bandwidth. Because depending on the how this link is loaded in real time, the actual bandwidth is in many ways, in most of the cases, is less than the theoretical bandwidth. Okay. However, when we calculate the costs, OSPF uses the theoretical bandwidth based on the type of the link, not the actual bandwidth. Okay. So this last slide here talks about this notion that the actual speed of a link is normally less than or it's different from the default bandwidth. So if the default bandwidth, for example, for Ethernet is 100 megabit or 100 megabits per second, but when you send actual data on the Ethernet, you get an actual speed of much less than that. This is, of course, because of many things. Because there might be like collision, there could be like protocol overhead, MAC protocol overhead, and so on and so forth. So the actual speed of a link is normally less than, or in many cases, much less than the theoretical speed. So we can, in any point in time, we can show the interface information to get the actual speed as well as the theoretical speed. So the show interface command can show you all the information about this link, including the default bandwidth and the actual real-time bandwidth at any point in time. However, in our case, we don't use the actual bandwidth in anything. So for calculating the metric, we just use the theoretical bandwidth. So any questions? So we, as I said before, we should pay attention to the differences between the two protocols. There are some similarities, even though they are in two different categories. So EIGRP belongs to the distant vector routing protocols, and OSPF belongs to link state routing protocols. However, as we have seen, there are some similarities, including the fact that they both use hello packets, they both use some type of request and response when they send the message updates, and they both use triggered updates when the topology changes. However, there are some major differences, including the fact that EIGRP uses distances and directions, whereas OSPF uses the concept of link state information, and it uses flooding and so on. Also, the metric for EIGRP is a composite metric that uses 4 different components. 2 of them are used by default, which are the bandwidth and delay, whereas for OSPF it uses only the bandwidth. So that's it. So